Hello friends, I welcome you in lecture number 14 on higher order partial differential equations. Up to lecture number 13, we have discussed shortcut methods for finding particular integral of non-homogeneous linear partial differential equations. But we know that shortcut methods are applicable for special functions on the right hand side, and we have discussed shortcut methods for this type of functions on the right hand side, that if right hand side is exponential function, if right hand side is in the form sin ax plus by or cosine of ax plus by, and if right hand side is a polynomial function in variables x and y. But suppose our right hand side is not any of these three functions, then we cannot apply these shortcut methods. So for that we have to understand another method which can help us to find out particular integral for any function on the right hand side. So today we are going to discuss general method of finding particular integral of this type of non-homogeneous equation, which we denote by f(d)z equal to fxy. And here also we are having one restriction, that this method is applicable if this function capital F of d and d dash is homogeneous function of d and d dash. So we are going to discuss that general method for finding particular integral, with the assumption that this f d dash is a homogeneous function of d and d dash. Now suppose f d dash is a homogeneous function of degree n, then we can write f d dash as the product of n linear factors. Suppose f d dash is a homogeneous function of degree n in d and d dash, then f d dash can always be written as the product of n linear factors of this type: d minus m1 d dash times d minus m2 d dash and so on, nth linear factors denoted by d minus mn d dash. So we can see that if f d dash is homogeneous, then this equation number 1 can be written in this form: d minus m1 d dash d minus m2 d dash and so on, d minus mn d dash z equal to fxy. So we have written equation number 1 in another form by expressing f d dash as a product of n linear factors of the form d minus m d dash. So from this, for particular integral, what we are doing, we are considering, we are interested in the solution. So z equal to 1 divided by this d minus m1 d dash d minus m2 d dash and so on, d minus mn d dash, that we operate on the right hand side. So how to operate these linear factors on the right hand side, that is our problem for this method. So for that, first we solve this equation. Suppose we consider one linear factor, say d minus m d dash, and z equal to fxy. So from this we will obtain z equal to 1 over d minus m d dash fxy. So we first try to find out solution of this equation for one linear factor d minus m d dash z equal to fxy, and then we will have formula for this right hand side, and then we will see how to write down this particular integral. Now as we know, this d and d dash are partial derivatives of z with respect to x and y. So this I can rewrite as del z by del x minus m d dash z, that is del z by del y, equal to function of x and y. And if you recall, we have used this notation. small p for del z by del x, small q for del z by del y. If you recall my lecture series on first order partial differential equations, then you will find out this type of notations. So here I replace del z by del x by small p and del z by del y by small q equal to say fxy. And if you have seen that lecture series on first order PDEs, we have discussed Lagrange equation. We have seen how to obtain general solution of Lagrange quasi-linear equation, which is having this type of general form: capital P into small p plus capital Q into small q equal to R, where p, q, r are functions of x, y and z. So you can see that this is nothing but Lagrange equation. If we compare this equation with this standard form, then we find that capital P is coefficient of small p, which is 1, capital Q is coefficient of small q, which is minus m, and R is function on the right hand side, which is f here. And we know how to solve Lagrange equation. For that we have to write Lagrange auxiliary equations, which are dx divided by p equal to dy divided by q equal to dz divided by r. So now we substitute values of p, q and r. Dx by 1, dy divided by minus m, dz divided by f of xy. Suppose we give this number 3. Now to solve this Lagrange equation, we can compare any of these 3 fractions. So suppose I consider first 2 fractions of equation number 3, then you can see I have dx equal to minus dy divided by m. So from this I can write this as dy, or I can write one more step, m dx equal to minus dy, or I can rewrite in this way also. If I take dy on the left hand side, I have dy plus m dx equal to 0, and if we integrate, we have y plus m into x, y plus mx equal to say c, where c is arbitrary constant. So here we give this number 4. Now suppose I compare first and last fractions, then I will have dx equal to dz over fxy. I am comparing first and last fractions of equation number 3. So dx over dz divided by fxy. But here you can see with dx I have constant function 1, but with dz I am not having function of z. So what I can do is I can write dz equal to fxy times dx. Then with dx I must have function of x only, but here I have function of 2 variables x and y. So for that we are using this first solution. From equation number 4 we can replace y by c minus mx. Suppose I consider I use this first solution. So here I find that y equal to c minus mx. So that I am writing here y equal to c minus mx dx. Okay, here I can write that by equation number 4 y is c minus mx. So we are using that c is equal to y plus mx. So now this is separable. So if we integrate both sides with respect to x, here I have integral of dz with respect to z is z. Here f is an arbitrary function of x, so I keep this as it is, f of x comma c minus mx integral with respect to x, and some another arbitrary constant can be written say b. So here we can see we have obtained the solution of this equation d minus m d dash z equal to fxy. But we are interested in the particular solution, therefore we are considering particular constant. Suppose we consider b equal to 0, or we are not writing arbitrary constant for particular integral. So you can see I have obtained this solution of this equation d minus m d dash z is nothing but z equal to integral of f of x comma c minus mx, and where we have used the fact that y is c minus mx. So this we will integrate with respect to x, and after integral we will replace c by y plus mx. So that is nothing but particular integral of this equation of first order, which is Lagrange linear equation. So from this I can write that where c equal to y plus mx. So this we will substitute after integration. So what we have discussed, that if we have this type of equation d minus m d dash z equal to fxy, then particular integral equal to 1 over d minus m d dash operated on fxy, and here we replace this y by c minus mx, where m is this value, and we integrate with respect to x. If we replace y by c minus mx, this becomes function of x only, that we integrate with respect to x, and after integral, after taking integration, we will replace c by y plus mx. So now you can observe that if we have homogeneous function of degree n, suppose f d d dash is a homogeneous function of degree n, then we will have this type of formula for the particular integral. So here from the right hand side we will operate each of these factors on the function fxy. We will start from this factor, then this factor, and so on. So and for that we will use this formula, that 1 over d minus m d dash fxy equal to f of x comma c minus mx dx. So remember this formula, which we have derived by solving the Lagrange quasi-linear equation, 1 over d minus m d dash operated on fxy. This is equal to integral of f of x comma y is replaced by c minus mx, and where c is to be replaced by y plus mx after integration. Now instead of m, suppose we have d plus m d dash, then here you can replace m by minus m. So you can remember only one formula. Here I replace m by minus m, and I have f of c plus mx dx, where c is going to be y minus mx. So we will remember this formula, and we will discuss problems related to this method in upcoming lectures. And for the time being, you must be familiar that how we have derived this formula, and you have to remember this formula, that 1 over d minus m d dash operated on fxy, where there is no restriction on fxy. So here we replace y by c minus mx, where this we have to compare our factor with d minus m d dash, and we have to find out what is m. Suppose my factor is d minus 3d dash, then I will take m equal to 3, and I will replace y by c minus 3x. So in short, we are converting this function of two variables x and y into function of only one variable x, and after integration we have to replace this c by y plus mx. So remember this formula, and this method is applicable for any function on the right hand side, but one restriction is that our function of d and d dash must be homogeneous in d and d dash. So this is all about this session. I hope you like it. Thanks for watching.